Hi everybody. So in this video today, we are going to do lab 11, which is the ripple counter, and I'll show you the circuit we are building. So that is the circuit we are building. It is a ripple counter with 3 output bits, and the least significant bit is here. The most significant bit is there. Okay, and one of the first things I'm going to do is put the pin numbers on my diagram. So what I have found is the data sheet. I've cut this out of the data sheet for the chips that I'm using. So this is the SN74LS73, which is a chip that contains 2 JK flip-flops that can be used independently. And because I need 3 flip-flops, I'm going to have to use 2 of these chips. So you can see on this diagram where they say 1 clock, 1 clear, 1 K, 1 J. They're referring to the first flip-flop. And then when they say 2, that's referring to the second flip-flop. And of course, the chip needs power and ground, which are actually on pins 4 and 11. So don't mistake that for having your usual power and ground positions as you're used to. Okay, so read the diagram carefully. So the first thing I'm going to do is to write the pin numbers on the diagram. And I'm going to have to choose which flip-flop is going to be number 1 and number 2 on each of my ICs. So I'm going to do that now. And so I'll show you this, although this is something you should actually also be doing yourself in the lab. And here's my chips. I have them ready to go. Okay, so there's my lab, and I have my pinout diagram. So I'm going to say that this is going to be on IC1. This is also going to be on IC1, but this last one will be on IC number 2. So this will be flip-flop number 1. So J is pin 14. The clock is pin 1. K is pin 3. Q is pin 12. And Q bar is pin 13. Okay, now this reset line is the clear on the pinout diagram, and it's active low, represented by a bar on the pinout diagram or a bubble here on my sheet, and that is pin 2. And because on IC2 here at the end, I'm going to use flip-flop 1 again. It's actually the same pin numbers, but it's on the other chip. So I can just write those in. 13. Okay. And for this middle one, that is on IC1, but it's the second flip-flop. So J is 7. K is 10. Q is 9. Q bar is 8, and the clock is 5, and the clear is 6. So I'm going to check those pin numbers again. J is 14, K is 3, clock is 1, clear is 2, Q bar 13, Q 12. Okay, and that would be pin 2 there at the end. Okay, so I think these pin numbers are correct, looking at the diagram and just matching things up. Now, the thing is, I am not going to build this whole circuit at once. I'm going to build it in stages and test it in stages. So to start out, I'm actually just going to build this first part of the circuit, and I'm going to test it. So I have my breadboard. These input switches are coming from these buttons I have here. I'm really only going to use one of them for my clock, to pulse my clock, because I know that the rest of the inputs are going to be held high. Okay, so here is one IC. And here is the second IC. Okay, and so the first thing I'm going to do is give each chip power and ground. Remember that power is actually coming in on pin 4. And because I have put power to my bottom red rail here as well, I can get power from there because I've already connected to power here and then through the other board here to my 5-volt supply, my fixed 5-volt supply. And then I need ground pin 11. So 8, 9, 10, 11. I'm going to go ground here. 12, 11. Okay, so that's connected. And then J and K, I'm going to tie high because they were tied to 1 on my schematic diagram. So I'm going to tie them to 5 volts. So J is pin 14, tying it to 5 volts, and K is pin 3 that I'm also going to tie to 5 volts. And actually I could use a tiny jumper for that because it's right beside pin 4, which is also tied high. So I can connect to power just like that with this tiny jumper, which doesn't want to go in. Tiny jumper is not working because I should probably be using a pair of pliers, so I use a slightly bigger jumper. And just connect pins 3 and 4 because 4 is also power. So I've connected those. Now the reset line, if it's set low, it will cause a reset, which would be to force Q to become 0. So I'm going to tie the reset line high for now. So that is pin 2, and I'm going to tie it high like that. Pin 1 is going to be from my clock, so that is going to be my push button. And Q0 is my output. Now that is actually going to drive the next flip-flop, but just for the purposes of testing, I'm going to connect it to one of my LEDs so I can test it. So let me give my other breadboard here power, and let me give my other breadboard here ground. Okay, so now that breadboard has power and ground. And I'm going to connect my output Q from pin 12 to my first light, wait, least significant bit, so I should connect it to this light. And so that is this input right here, and I'm going to put that to pin 12. 14, 13, wait a minute here, what have I got? 14, 13, 12, okay. And 11 was the ground. Okay, so, and pin, the Q bar output is not actually used for anything right now, so I'm not going to connect it to anything. And so what I want to do now is to power on my power supply. Now my Q light is off. Notice all these other lights are on because they're floating inputs. So actually what I might do right now is just ground them all so they're not connected. So let me power off and just ground all of those so that we don't get extra inputs happen, like extra lights on when we don't expect it. And this is just taking the place of the LEDs on your logic board, since I don't have a logic board here with me at home. So I'm just grounding all my LEDs. Okay, so now when I turn my power supply on, all the lights are off. Now, if the light wasn't off, I could reset it by taking this clear line, which is set high right now, momentarily setting it low, and then putting it back high. Ideally, I'd be doing that with the switch, so I'm never like in an indeterminate state, but for now, we'll leave it tied high. Now, what should happen is, because this is a negative edge triggered flip-flop, when the clock edge falls, the output Q should toggle. So if I push my button down, that makes the button high. When I release the button, it gets this falling edge, and output Q should toggle, which means it should become high. And you saw the light output Q light, which looks white there on the video, but is actually red. The light goes on. Now, if I push this clock high again and let it fall again, the light should now go off. And if I push it high again and then release it again, the light should go on. So notice every time I release the light, which is a falling edge, the light changes state. And so that is the flip-flop toggling, and so I know my first flip-flop stage is working. Okay, that's important. You don't want to build the whole circuit only to find out that it doesn't work, because then you don't know where to troubleshoot. And this way I verified that this part of the circuit works. Now, if I set this circuit up with the next part of the circuit and this part of the circuit stops working, I'm going to suspect that it's a future part of the circuit or the next stage that I connected to that was actually causing the problem, and not the first part. And so that gives me a little hint when troubleshooting, and that's why I'm connecting the circuit in stages, not all at once. So I'm going to turn my power supply off now, and I'm going to connect the second flip-flop, which is on the same chip, but using the second flip-flop pins. Okay. Okay, so now this output Q, instead of, I'm still going to have it drive a light, actually, because that's still my least significant bit output. But I'm also going to have this Q0 drive the clock of the next flip-flop, which is on pin 5 of this chip. Okay, so that's going to go to pin 5. It's getting a little crowded in here, but follow along as best as you can, in your mind at least, or on the diagram. And actually, this is another another hint that some people will do as they're connecting, as they're wiring up things on their wiring or on their schematic diagram. They will check off the line. So I haven't done that here, but I just connected this line. So I could check it off or highlight it so that I know I've connected it. And that's a good way of keeping track while you're connecting things in your circuit. J and K for this middle flip-flop also have to be set high. So that's pin 7 to be set high. And pin 10. So 8, 9, 10. So pin 10 also set high, and I've powered both red rails of my logic board so I can go up or down to red for high for 5 volts. The reset line on pin 6 also has to be set high. And now if I had a wider selection of small jumpers here at home, I could make this look a little neater. I could cut myself some new wires or buy pre-cut jumpers. And I'm really just using the long wires to save a bit of time here. I've just connected pin 6 to high. And so the only other connection I have to make for this flip-flop is I have to send pin 9, which is Q1, to the LED, and I'm going to send it to this one, which is my next most significant bit. So that's on pin 9. Okay, and that is going to go now to this LED. Okay, now the important thing here, and let's look at the diagram again. The important thing here is that connection from pin 12 to pin 5. It's showing that the output of the first flip-flop is the clock that drives the second, which means when this Q bar has a falling edge and goes from high to low, that's when Q1 will change state, okay? So let's turn on the power and check our circuit again. Okay, so let me force a reset to see if this light is on because of a reset issue. So that's pin 6 here. I'm going to put it low to force a reset and then back high, and you see that I am now reset, no lights are on. I'm going to push the clock, and there's Q0 coming on. Now when I push the clock again, Q0 should go off. When Q0 goes off, Q1 should come on. And it does. And now I'm going to turn Q0 on by pushing the clock again. And now when I push the clock again and Q0 goes off, it's going to trigger Q1 to also go off. Okay, so now you can see with just 2 flip-flops hooked up and 2 lights as my output bits, I have a 2-bit counter. So with the lights off, that's 0. There's 1, there's 2, and there's 3. If I'm counting in binary, and this is more significant side and this is the least significant side, okay? So great, circuit is working perfectly so far. All I have to do is add in my 3rd flip-flop. So I'm going to turn the power off and add in my 3rd flip-flop. Now remember, my 3rd flip-flop, because there's only 2 flip-flops on each IC, my 3rd flip-flop is actually on the 2nd IC here. So I have to also give that IC power and ground. So power being pin 4, and ground being pin 11. Okay, so there's power and ground. I'm a little bit short on wires here. And I need J and K, which is pins 14 and 3, to also be set high. So I'm going to have pin 14 high and pin 3 shall be high. Okay. I'm also going to need the reset line, which is pin 2, tied high. And I may need to, you know, I may need to make it go low for just a second if I need to do a reset. But for now, it is tied high. And what I could do, what I should do, is actually tie all the resets together and just have the ability to reset with one wire. So I can do that here if I put pin 2 from here and pin 2 from this chip. And pin 6 from this chip. So you can see I've got all the reset lines tied in this one row, and then I can actually just go from that row to high, and then if I want to do a reset of all the lights, I can reset them all just by dipping this signal low for a second. So now I need to send my output Q2, which is on pin 12. I need to send it to this, this third LED right there, which is going to be my my most significant bit for my 3-bit counter. Okay, so let me power on. And that second one is on again. So I'm going to do a momentary reset by taking my reset line here and putting it low for just a second and then back to high. If I left it low, the outputs would just continue to be forced low. So I have to set it back to high so it doesn't interfere with my circuit. And now if I press my clock, all lights are off. That's 0, 0, 0. I get 1, 2, 3. I should be getting 4. I should be getting 4 and I'm not. So the question is, you know, where is the problem? Is it a missing wire or a broken wire? The first thing I'm going to do is power off and check my connections. So I realized that I did not tie my output Q1 to the clock of this chip. So I need to make a connection. And this is where, if I had been good and or maybe a little bit wise and checking off my connections as I made them, I would have seen that I forgot to connect this pin 1, the clock input, to pin 9 of the other chip, the Q1. So I need to make that connection, right? So if I show you on the diagram, I'd forgotten to make this connection here with the output of the second chip driving the clock of the third chip. So obviously without that connection, it's not going to work. I've turned the power back on. I'm going to take the reset line and put it low to reset the outputs so they're all 0. Then I put the reset line back high again. Now I'm going to push I'm going to push my clock button here, and I have 1, 2, 3, 4, 5, 6, 7, and back to 0 again. So my 3-bit counter is counting, right? 1, 2, 3, 4, 5, 6, 7, back to 0. So it is counting in binary from 0 to 7 and back around again. So in the lab or in your lab book or lab printout, what you're going to do is you're going to fill in the table there showing the outputs for the sequence of clock pulses that I just did. Okay. Okay, so what I'm showing you now is a different camera angle with showing the test equipment. So I've got, you know, my power supply here, and I'm using the fixed 5 volts. I've got a function generator up top here, and I've got the oscilloscope over there on the side. And what I've done right now, I don't have the green logic board here at home, so I've hooked up the function generator to act like the 1 hertz pulsar input that you can get from the logic board. So, and with this model of function generator, you cannot set the amplitude with a number, okay? You have to set it by looking at the waveform on the scope. So I'm going to try to bring it into camera view here. You can see I've connected the scope cable and the mic and the function generator cable red to red, black to black. So I'm going right now directly from the function generator to the oscilloscope, okay? And then what I have to do is set the amplitude. So I've already set it up there, but what I did was I changed the amplitude by changing this button here. Okay, that changes the amplitude. I need it to be a 5 volt amplitude, so from top to bottom of the waveform, 5 volts, because I want to use it as the input to this chip, so it's got to be 0 to 5 volts. However, by default, this offset button is pushed in and set to 0, so by default, that 5 volts would go minus 2.5 volts to plus 2.5 volts, but I actually want it to go 0 to 5. So what I had to do was pull out the offset button and change it while watching my scope. So looking at the scope here, I've set the ground line there, and by changing the offset, you can see that I can move this waveform up and down. So I had to turn the offset knob to lift the waveform up until the bottom of that waveform was at 0 and the top is at 5 volts because I'm at 5 volts per division. So one big division is 5 volts and I'm at 5 volts. Now I didn't use that scale to set the 5 volts. When I set the 5 volts, I actually had this on a bigger scale. I actually had it on the 1 volt scale, and I had the graph moved down, because when you're on the smaller volts per division, the waveform is bigger, and you can actually get a more accurate sense of whether you really are at 5 volts. So when I lined it up there, I was like, okay, that is definitely 5 volts. So then I'll go to my 5 volt per division setting. And I could have left it at the 2 volt per division setting here, but I couldn't keep it on 5 because where I had set the ground line, it would have gone off the screen. Now, with it here set at 5, my ground line is now here because with the position knob, I moved it down. So there's my ground line and I have my 5 volts. Now that would normally be the most accurate way to read this, but because I'm going to end up putting multiple waveforms on the screen, and I really just need to see high-low, not exact values, I am going to change this to the 5 volts per division setting, which means that my waveform looks smaller because now one little square is the full 5 volts. So I'll move this waveform up and there's its 0 line and 5 volts. And remember, that amplitude I set by changing this amplitude knob. And I had to observe the amplitude change on the oscilloscope. With this function generator, there's no way to know what that is unless you're looking at the oscilloscope. Now, right now, the frequency is set to roughly a kilohertz. I don't need the frequency to be that fast because at first I want it to be at 1 hertz to see it with my eyes. But 1 hertz that we can see with our eyes, that change, once it's connected to our circuit, is too slow to be seen on the scope. So I set it to a higher frequency to set up the output on the scope. Now I'm going to put it to 1 hertz. So I click the 1 hertz scale, and I can change the frequency here. Oh. So there I'm at about 959 millihertz, which is close enough to 1 hertz. I could sit there and adjust the knob a little bit more, but I don't really need it to be that accurate. I just want something slow enough that we can see with our eyes. So what I'm going to do now is switch to the other camera, and I'm going to connect that function generator output to our main clock signal. Okay. Okay, so there's my circuit again, and I've got a cable in the way here. Let's see if I can just move this cable out of the way. Okay, so what I'm going to do is I'm going to take that function generator input, and I am now going to connect it to the clock of my circuit, which means I'm not using the button anymore. So I will take that wire from the button, and I will give it the red lead here of my function generator, and the black lead goes to the same ground that everything else is grounded to. I could accomplish that by putting, actually I could just clip on to one of these resistors, which is actually grounded. Okay, so now I have a 1 hertz signal, and I can see my output doing strange things, but I suspect that the circuit wasn't reset well. So what I'm going to do is reset the circuit. Let me bring the lights into the camera view there. You can see that that the 1 light is just blinking. So I'm going to reset my counter circuit. Everything goes to 0, and then this is very strange. I can see that stuff is blinking, but not at the frequency that it should be, and not all the lights. Very, very interesting. Okay, so to troubleshoot that, I'm going to disconnect from the function generator and go back to my button and see, does it still work correctly if I use the button? And I better make sure I'm connected to the right spot there. And I don't see my circuit working anymore. So I'm going to start troubleshooting my circuit. The first thing I should check is that do I actually have, am I actually getting the 5 volts I need at the clock input? So I'm going to take this signal from my push button and just test it with a little voltmeter that I have here to see if I'm getting my 0 and 5 volts out of this. This is a little bit tricky because I have to hold the test leads and push the button at the same time, which is a little bit of a disadvantage of not having a actual switch. Okay, and I'm measuring and I'm not getting my 5 volts, which means I may have a broken wire or a connection issue there, and I'm going to troubleshoot that. Okay, so I turned the camera off there for a second while I went to get a set of alligator clips just so that I could clip on to where I was testing. And you can't see my meter because it's off the screen right now, but I measured and I realized, yeah, I'm not getting output from that button. And then I realized, oh, that's because I did not have the power supply turned on. Classic mistake, but easily found with, you know, by measuring voltages. And so I have actually turned the power supply back on now. And I'm just pressing the button here to see if the circuit will still work. Right now the clock is not connected again, so I'm going to connect the clock because I had removed that wire to test it. I'm going to reset the outputs, okay, and keep my reset line high now. And then I'm going to push the clock button and watch the outputs. Okay, so the outputs are still working great. And not having that power supply on previously would definitely have affected things because my chips wouldn't have been getting power, and that's bad. So let's disconnect that clock input from the button and connect it back to the function generator. So my function generator, I'm going to connect to ground, and I'm going to connect this pin 1 now to the function generator. And now you can see, I don't even have to reset it because it's been busy counting, although I think it's counted starting in the middle. You can see that now it is counting and it is driven by the frequency of the function generator. 0, 1, 2, 3, 4, 5, 6, 7, 0, 1. Okay, so we set it to roughly 1 hertz. So, so if the clock is set at 1 hertz, then Q0 is changing at 1 hertz because it's changing on the falling edge. Okay, but that means the frequency of Q0 is actually is actually half of that of the clock, right? So I'm going to make a change on the function generator. You can't see what I'm doing, but what I'm going to do is turn up the frequency dial so that I'm going to turn up the frequency dial, and you will see the speed of counting increase, okay? And I just want to show you, so here I'm turning the frequency dial slowly, but you can see that the counting is getting faster and faster. And now I've reached I'm at about 3 hertz right now. If I go up to 10 hertz, so there's roughly 10 hertz. If I go up to about 30 hertz, you can still see it flickering. If I go up to 100 hertz, you can still see some flickering on the video, just the way it's being recorded, but in real life, I cannot see that flickering. Okay, it looks solid to me in real life. If I go up to a kilohertz, now it even looks solid for the video. But having a frequency of 1 kilohertz will allow us to look at these output voltages on the oscilloscope. So I'm going to switch cameras now and go over to the oscilloscope so we can look at some of the output waveforms. Okay, so I'm sitting at roughly a kilohertz. And now I'm going to connect my scope to some of my outputs. And I'm going to use 2 channels of the scope so that you can see multiple outputs side by side. In step 6 of your lab there, it says use the oscilloscope to measure the frequency of the clock input. So yes, we definitely want to look at the clock input. Let's connect that to channel channel 1. Okay, I'm going to connect that to channel 1. That is the clock input, which is also coming from the function generator. So I'm connecting a red lead of my scope to the red lead of the function generator, and I'm connecting ground to ground. Your scope leads are always going to go to ground, no matter what, okay? The scope lead, the black of the scope lead always goes to ground. Now, there's my waveform back on the oscilloscope. As a rough, you know, not super accurate, but good enough for us calculation of frequency, I can see that the times per division is 500 microseconds per major division, and I can see that one waveform is taking up 2 major divisions. So that is a millisecond for the period, and frequency is 1 over period, so that is a kilohertz. So I do have a kilohertz waveform here for my clock. Now I am going to measure something else on channel 2. So I am going to put channel 2 onto Q0 so you can see for yourself how Q0 looks compared to the clock. So I am grounding the other channel of the scope, and my second red lead of channel 2 of the oscilloscope, I'm going to connect to Q0. I'm going to grab an extra wire to do that. So Q0 is my least significant bit there, which is the same as right here. Okay, and then I'm going to tell the oscilloscope to display channel 2. Now channel 2 is set at 50 millivolts per division, which is way too small. I'm going to set it to the same 5 volts per division as channel 1. I'm also going to go to the trigger menu. It's edge triggered. I'm going to trigger it off channel 2 so that the channel 2 waveform doesn't look overlapped like that. And so now you can see the top signal on my scope is the clock. The bottom signal is Q0. So you can see for every falling edge of the clock, Q0 toggles. Falling edge of the clock, Q0 toggles. Falling edge of the clock, Q0 toggles. And you can clearly see that Q0 is has a frequency that is half the clock waveform, right? It's a slower, Q0 is a slower waveform. Now I can repeat these steps to measure Q1 and Q2. Now, unfortunately, I don't have a 4-channel scope, so we can't see them all at the same time. What I will do is I will take the clock signal off of channel 1 and I will connect it to Q1 so that you can see Q0 still here on the bottom, and I'll put Q1 on the top so you can see them in relation to each other. Okay, so I've taken the clock signal off, and I'm now putting this channel of the scope onto Q1. Let me make sure I'm in the right spot here. I'm going to disconnect it from my lights for a second and connect directly. Q0 is not, or Q1 is not showing up. Let me take a look at Q2. There's Q2. I'll make that clearer in a second. My Q1 is not showing up. And I don't know if it's because I've got a broken wire. I'm going to try changing this wire. So Q1 is on pin 9. I'm going to take a look at Q2 again. So there's Q1, Q0, Q1. This should be Q2. Yes, which is here. There's Q2. Now the weird thing is my Q1 signal is not showing up, but I know it's still there because it's driving the clock appropriately to show Q2. And you can see Q2 is 4 times as slow as Q1, right? Because, or sorry, as Q0, because Q0 cut it in half, and then Q1 cut it in half, and then Q2 is half again. So the top signal right now on the scope is Q2. The bottom signal is Q0. I just want to see if I can get Q1 to actually show up there. So I'm going to try to put Q1 on channel 1, so, or sorry, on channel 2. So I'm going to lose the bottom plot, which is Q0. And I'm going to try to put channel 1 there and Q1 there. So there it is. There's Q1 on channel 2 and Q2 on channel 1. So top waveform Q2, bottom waveform is Q1 right now. And if I move the bottom waveform back to Q0, there's Q2 on top compared to Q0 on the bottom. And if I put the bottom back on the clock, you can see the clock compared to Q2. Okay, so the tricky thing is we can't see them all at the same time, but you're able to see them in relation to each other. And of course, if we were looking at the times per division, we could record those frequencies. You know that each one is half again. So the least significant bit has half the frequency of the clock. The next bit has half the frequency of the previous bit. Okay, so you should be able to fill in your numbers for steps 8 to 10 of the lab. Okay.